Okay, 6.2 vector addition. In this section, we will examine ways that vectors can be used in different physical situations by applying vectors to a variety of contexts. Okay, so to determine the sum of any two vectors, say for example, vectors A and B, what we want to do is we want to arrange the vectors tail to tail. Okay, so this is important. And then complete the parallelogram formed by the two vectors. Their sum is the vector that is the diagonal of the constructed parallelogram. So first what we do is we draw these two vectors A and B, and we draw them like normal. And right now, this right here is tail to tail. Okay, but we actually don't want it tail to tail. What ends up happening is we take this vector here, or vice versa, we can take either one. The addition of two vectors is always going to have the same, it's called resultant, right? This pink vector here. Okay, so we take this and we physically, like we pick it up and we go head to tail, tip to tail, tip to tail, or head to tail. Okay, and all that means is that like at this head, we take this and we put the tip, like we put the end point here, and then whatever that yields, so from the start, so this right here would be like the start, and then we go across and we draw an arrow, and then this would be the end. So this red vector, that would be A plus B. That's called the resultant. Okay. So the sum of the vectors A and B is also found by translating the tail of vector B to the head of vector A. So that's kind of what I did up there. The resultant is the vector from the tail of A to the head of B. Okay, so you can do the full parallelogram, or you can simply just pick up the vector, or like draw one vector at a time. So maybe draw A first and say, okay, now I'm going to start the next vector here, draw B, and then we're done. Okay, so kind of like just continue drawing vectors. So to think about A minus B, what we can do is arrange the vectors tail to tail. Okay, A minus B is the vector that must be added to B to get A. This is a vector from the head of B to the head of A. This vector is equivalent to A plus negative B. Okay, so when I think of this, I think, okay, our A is going to be normal, right? It looks like that. That didn't really change, right? But instead of adding B, which goes this way, okay, so if B was like this, what we do is negative B. So if normal B is like this, so this is B, negative B goes in the opposite direction. Remember, same magnitude, opposite direction. So if we went A being normal and then we added negative B, we would essentially end up with this vector. So like, again, this is the start, this is the end, and our vector resultant would be like this, okay? So you can either do it continuation, so tail to tip, and then draw the resultant, or you can draw it the way it's saying when we have a negative B, you can draw it tail to tail. Okay, both tails coming out, and then that works too. So the parallelogram law of adding two vectors is kind of what we went over. Okay, so this is the law. To determine the sum of two vectors A and B, complete the parallelogram formed by these two vectors when placed tail to tail. Okay, so place them tail to tail, one goes up, one goes over, okay? And their sum, so then we're going to complete the parallelogram. Their sum is the vector AD. Okay, so we can see this here, this is the resultant. the diagonal of the constructed parallelogram. So we already talked about this, but now I'm actually saying this is actually called the parallelogram law for adding two vectors. Okay, so when dealing with two forces that act on an object, we denote the first force as F1 and the second force as F2. And we can use vectors in this case since the force that acts upon the object has both a direction and a magnitude. Okay, so force is a vector. We use theta to denote the angle between two forces. We can use these in such examples as two supports hanging from a ceiling, two children pulling a sled, two trucks towing a car, etc. And we're going to take a look at some of these examples. So when we draw a diagram, we consider the following. So first we consider the direction of the force exerted by each of the forces. Okay, so direction is indicated by the direction of the arrows. Okay, so wherever the arrow is, that's the direction. Okay, that versus that. Okay, the magnitude. We also consider the magnitude of the force exerted by each of the two forces, okay, is proportional to the length of the corresponding force vector. This means that the longer the force vector, the greater the exerted force. Okay, and the forces that have been exerted have been applied at a common point on the object. Okay, that's the assumption. The resultant will be the direction of the object and the force at which it is moving. Okay, so the resultant is, of course, a vector as well. It's going to have a direction and a magnitude. To find the single vector, we combine F1, so the first force, and F2, the second force, by drawing a parallelogram determined by constructed vectors. The main diagonal of the parallelogram is called the resultant, or the sum of the two vectors, and represents the combined effect of the two vectors. So, example 1. Given vectors A and B such that the angle between the two vectors is 60 degrees, and the magnitude of A equals 3, and the magnitude of B equals 2, we're going to determine the magnitude of A plus B. So what we want to do is we want to draw A and B. So A and B. B is a little bit shorter, okay, because B has a magnitude of 2 and A has a magnitude of 3. And the angle between these two is 60. Okay, this right here is not the resultant. Okay, it can't be. And the reason why it can't be the resultant is because we're right now tail to tail. And we know tail to tail, that would only be the resultant if it was A minus B. So instead, we need to pick up our B. So this is vector A, this is vector B. We need to pick up our B, and we need to go tail to tip, and then tail to tip. And this is going to be our resultant. It's going in that direction. Okay, so let's label this. B is 2, A is 3. So if we actually just focus on what we're dealing with here, we have 3, we have 2, and then we don't know the resultant. Oops, arrow. Okay, so when we're talking about the angles, here's the thing. So in a parallelogram, so say we finish this parallelogram, okay? In a parallelogram, the diagonals, I don't believe, actually bisect the angles. So this is not necessarily 30-30. Okay, so if we draw this resultant, we're going to need to find this angle so that we can draw it in here. We need A angle, okay? Or even better, we're actually going to solve for this angle. So we know in a parallelogram, these two angles here, I'll do this in yellow. These two angles here are going to be the same. Okay, so this one and this one are going to be the same. And then maybe in purple, this one and this one are going to be the same. So formally, if we have a quadrilateral, we have 360 degrees, and we know these two are 60, like that one would be 60 as well. So 60 plus 60, and then these two would be x plus x. So what we have is 360 equals 120 plus 2x. So we're going to have 240 when we bring over the 120. 240 equals 2x. So mathematically, we have like x equals 120. Okay, so by solving for that, we're going to have the 120 here and 120 here, which is fine in the parallelogram. But then what you want to do is when we actually draw, like, and we focus in on what we're dealing with, this one right here is going to be 120. So at this point, we have two side lengths and the contained angle. So what we have is cosine law. Okay, let's just call this capital A, capital B, and capital C. So we're going to solve for the resultant, which is, oh, I don't like that. I'm going to call it XYZ because we used A and B over here. So we're going to solve for side length Y. So the formula that we use is y squared equals x squared plus z squared minus 2xz cos 120. Or let's go cos capital Y. So we're going to have y squared, which we don't know, that's what we're solving for, equals, okay, we have x squared, so x is going to be opposite x, that's 2. Okay, 2 squared. Z is going to be opposite z, which is 3 squared, minus 2, 2, 3, cos 120. And if you remember, these two numbers here actually repeat here. Okay, they're both xz. So if we put this entire calculation into our calculators, so 2 squared plus 3 squared minus 2 times 2 times 3 cos 120, I get 19. Okay, so 19 is y squared, but we only want y, so we get y equals 4.36. So going back up to the original question, this doesn't ask for the direction of the resultant vector. This just asks us to determine the magnitude of a plus b. Okay, so the magnitude of a plus b, again, this is the resultant, and you want to find the length, which is like aka the magnitude. So it's not necessary to draw a parallelogram each time. So we can use the triangle law of addition. Okay, so this is just like half the parallelogram law. So the triangle law of addition, this is more the one that I'll use in this class. In the diagram, the sums of the vectors a and b, so in other words, vector a plus vector b, is found by translating the tail of vector b to the head of vector a. Okay, so they have vector A here, vector B here. So they just picked up B, they took the tail, they located it at the head of vector A. So now we have vector A and then vector B, like that. Okay, with this again being the resultant. This could have also been done by translating vector A, so that its tail is the head of vector B. Okay, so what this is saying is this follows associative law. Vector A plus vector B is going to equal vector B plus vector A. Okay, you're going to get the same answer. So in either case, the sum of the vectors A and B is vector AC. Okay, AC. Okay, now the zero vector. So what the zero vector is it's a vector with a magnitude of 0. Okay, so when two opposite vectors are added, the resultant is the zero vector. So in other words, if this was vector A, and then this is vector negative A. Okay, if we drew those on top of each other, so we would draw vector A and then vector negative A, it would come back to the start. So it would have a magnitude of 0 because you went there and back. You returned to the exact same place. Again, magnitude of 0, which actually means that there's no direction. Okay, the 0 vector has a magnitude of 0 with no defined direction, i.e., okay, so the 0 vector is written like this. So the magnitude of the 0 vector is 0. Example 2, suppose you are given the vectors A, B, and C as shown below. Using these three vectors, sketch. So this is what we're going to sketch. We're going to sketch A minus B and then plus C. Okay, so let's start with A. So A looks like this. So we're going to do the same. We're going to go on the same angle for like the same magnitude. Okay, so this is going to be A. I did this too high because now I'm like visualizing the answer. Okay, I'm going to put A down here. Okay, so this is A. Now we have minus B. So we can do one of two things. We can go tail to tail, but I don't want to do that. I want to do the opposite direction of B. So I want to do negative B. Okay, so that's A. And then B is not as long because the magnitude is a little bit shorter. So this is going to be negative B. Okay, and then we have plus C. So C is going north or like up. Okay, and magnitude approximately like this. So this is C. So our resultant vector is here. So this is A minus B plus C, all vectors. Okay, so the difference of two vectors, A minus B. So in the diagram to the right, the difference between vectors A and B is found by adding the opposite vector. Okay, B to A, using the triangle law of addition. So again, if this is vector A and this is vector B, then we know that this here is going to be vector negative B. So A, B, and then we have the pink as the resultant. Okay, example 3. In the rectangular box shown below, okay, OA, and usually O represents the origin. Okay, OA is going to be A, like vector A. Vector OC is going to actually be vector B. And OD, so OA is vector A, OC is vector B, and then OD here is vector C. And remember, these are in order. So OD starts at the origin, and the arrow is pointing toward D. Okay, OC again starts at the origin, points towards C. Okay, so what we're going to do is we're going to express each of the following vectors in terms of A, B, and C. Vectors A and vector B and vector C. So if we wanted to express BC, B is right here, and C is here. So this is the vector that we want to express. Okay, this is going to have the same magnitude of OA, or sorry, let's quote it with A. So vector A, except for it's going to be in the opposite direction. So vector BC can also be written as negative vector A. Okay. Now, vector GF. So let's find G and F. So G going to F in that order. Okay. A vector with the same magnitude is again going to be A, and it's going in the same direction. So vector GF is equivalent to vector A. Okay, now they start to pick up a little bit. Vector OB. Vector OB goes across. That's going to be a resultant. So what we'd have to do to achieve that resultant is add vector A to here, and then vector C. And it's just very nice that these vectors are going in the like correct direction, the direction of OB. So vector OB is going to be equivalent to vector A plus vector B. Okay, now D, vector AC. So A's here, C's here. So we would have to go from A to O, which is going to be negative vector A. Then we have to go O to C, which is going to be normal B. Okay, so we're going to go negative vector A plus vector B. Negative vector A plus vector B. Okay, now BG. So B starts here. G is in the opposite corner. So what we have to do is we have to go up and across, okay, to get that resultant. So going up is going to be vector C, and then going to the left is going to be vector negative A. So this is going to be vector C, and this is going to be negative A. I'll erase that to keep it clean. C minus A. C minus A. Okay, last one, OF. So it's from the origin all the way to the other side. This is actually 3D. Okay, so vector A, and this is the last one, so I can keep this on here. Okay, then we have to go plus vector C, and we have to go up. Oh, sorry, this was vector B, plus vector B, and then plus vector C. Okay, so these two can be expressed as each other. Okay, so bearing, the direction of an object measured in degrees from due north, okay, such as 160 degrees. So what this means is that if we had the compass, never eat shredded wheat, okay, we would start due north. Due north means like we would start like here, going up. Maybe I'll make this lighter. You see it on top of this purple, going up. And then if we rotated, say 160 degrees, okay, this would be 90. This would be 180 from due north. So it'd be approximately here. So this here would be 160 degrees rotation. Okay, that's what a bearing is. So when calculating the velocity of an object, such as an airplane, the velocity must always be calculated relative to some fixed object, okay, or some frame of reference. For example, an airplane can be traveling relative to the ground, or relative to another airplane, or relative to the wind. Okay, so it's always going to be relative to something. Okay, when we measure velocity relative to the ground, it's referred to as ground velocity. So that's just like a special definition or a special wording that you're going to see. Okay, so let's try example 4. An airplane heads due south. Okay, so inside of my paper, I always go never eat shredded wheat. Okay, so an airplane heads due south at a speed of 300 kilometers per hour. Okay, so we can go like this. Here's the thing. This is not a magnitude. This is a rate. It's kilometers per hour. Okay, we don't know how long this airplane is traveling for, so we can't say exactly what the magnitude is yet, but 300 kilometers per hour. Okay, and meets a wind from the west. Oh, I'm going to put this on the other side so it fits better. Okay, so this is going to be 300 kilometers per hour. Now, if we have a wind from the west, that means it's coming from over here and it's going toward the east. Okay, so this wind is 100 kilometers per hour. Okay, so both of these are a rate, 300 kilometers per hour, 100 kilometers per hour. Okay, so both of these are in a velocity. So the question is, what is the resultant velocity of the airplane relative to the ground? So here's the thing, because both of these are already in a velocity, our resultant, which is right here, is also going to be expressed in a velocity, so then it works. Okay, so we know that this is going to be 90 degrees because we're not talking about any other angle. We're talking specifically south and west. So these are going to be 90 degrees to each other. So we do not know what this one is. Let's call this theta. So what we can do is we can say, okay, this side is going to be opposite, and we're going to use SOHCAHTOA. This side is adjacent, and this side is the hypotenuse. So in SOHCAHTOA, let's use 100 and 300. We know that it's going to be tan theta equals opposite over adjacent. So our tan theta is going to be 100 over 300. So what we want to do is we want to say, okay, well, theta is going to be the tan inverse of 100 over 300, which is just 1 over 3. So theta is going to be 18.4. Let's just round to 18. Let's go 18 degrees. Okay, so in this diagram, theta is going to be 18 degrees. Okay, so let's come back to that. Okay, let's talk about the magnitude now. So we can do this one of two ways. We can either use 18 and either 100 or 300 with SOHCAHTOA to find r, or we can simply use Pythagorean's theorem. Okay, so let's call this vector s because it's going south, and then let's call this vector e because it's going east. So the resultant vector is going to be the magnitude of the southern vector plus the eastern vector, like squared. So, oops, that's r squared. So vector r squared is going to be 300 squared plus 100 squared. Okay, which is going to be 100,000. And then we want to square root both sides, so we get vector r equals 316 kilometers per hour. Okay, so what this means right now is that this resultant is traveling at 316 kilometers per hour. Okay, because say, for example, the airplane is going south, but then it's getting pushed. So it's actually speeding up from the wind. Okay, it's getting pushed to the right, like east, 100 kilometers an hour. So see how we have like 300 and 100? It is speeding up from that wind because it's going 316 kilometers an hour. Okay, so when we take a look at our therefore statement, here's the issue with the angle. This angle is just the angle in the triangle. We would have to, from the beginning, like the airplane leaves here, we would have to actually, what I do is draw a compass here, never eat shredded wheat, okay? And we have to actually calculate this angle, because this is like we quote these angles in bearings, okay? So if this in here is 18 degrees, let's call this angle phi, okay? So angle phi is going to be, so this here would be 180 degrees, but then 18 degrees we're not going to take into account. So it's 180 minus 18, and we are going to get 162 degrees. And that's a bearing. Okay, so our therefore statement is going to be, therefore, the airplane is heading at a 162-degree bearing at a velocity of 316 kilometers per hour. Okay. Because this is a vector, we need the direction, which is a bearing of 162 degrees, and we need the magnitude, which in this case is quoted by a velocity.